All right, hello there. So today we're going to do section 12.3. Hopefully you know a lot of this stuff from pre-calculus. And again, you can kind of jot down notes as we go along, or you can on a piece of paper, or you can print out this PDF. If I were you, I would advise you to print it out like 2 pages on one sheet type of thing on your printer settings so that you don't use up so much paper. And or like I said, you can just print out the written version of my scribble scratch here, but however you like to do it. All right, so first of all, the dot product of 2 vectors. So I'm just going to give you 2 vectors here. I got vector u is 3, -5, and 1, and vector v is 0, 4, and -2. All right, so when you do the dot product of 2 vectors, what you end up doing is you basically multiply the x's, the y's, the z's, and you add them up. And so in doing that, you're going to get a number. Okay, so 3 times 0 is 0, plus then I get -20, plus -2, so I get -22. So recognize that this answer right here is called a scalar. All right, so it's not another vector. Later when we talk about something called the cross product, when you do the cross product of 2 vectors, it is a third vector. All right, so this is important that you know the dot product is just a scalar number. It's just a number, like a constant that you end up getting. Okay, all right, some little properties to recognize here. If you have a dot a, that is the magnitude of a squared. We'll talk about that later. A dot b is the same as b dot a. Here there's like distributive property, so it doesn't matter if you do like a dot b and then add a dot c. And here, this is like associative property, that c can be moved anywhere. So you could do c and then a dot b, or you could do a dot c and b together first, so the constant can go anywhere. And the last one, 0, the 0 vector dotted with a vector always comes out to the 0 vector. All right, there's a few examples here. So in letter A right here, I have a dot product of u and v, and then multiplied by w. So remember that this is going to produce a number, a scalar. So why don't we just do that up here? So over here, u dot v. So I would get -2 times 3, so I get -6. So -6, and then 4 times -5, so -20. And then -1. So I get -27. So what I'm end up getting is -27 multiplied by w, which is 0 to -4. All right, so I end up getting 0, -54, and then 108. Okay, so I'm going to leave letter B for you to do right now. All right, so you should have gotten there. You had u, which is your -2, 4, and 1, and dotted with 2v. So 2v would have been 6, -10, and -2. And so you dot those together, you get -54. All right, this last one I want to explain because it has to do with this guy up here. So let's do v dot v. So v dot v is going to be basically 3, -5, -1, dotted with 3, -5, -1 again. So I end up getting 9 plus 25 plus 1, which is the square root of 30. Just 35. So notice if somebody had asked me for the magnitude of v. If you ask me for the magnitude of v, what I end up doing is I square this, I get 9, I square that, I get 25, and I square this, I get 1, and I add them up. So I end up getting the square root of 35. So just notice here that the dot product of a vector with itself is just the magnitude squared. So if I had done the magnitude of v and squared it, I would have gotten the square root of 35 squared, which is 35, which matches this. So that's just like a little rule. All right, this next piece, angle between 2 vectors. So the angle between 2 vectors, you should recognize this formula as well. It goes like this: cosine of your angle is a dot product of your 2 vectors over their magnitudes multiplied together. And you can use u and v or a and b, whatever. So this one down here, I get my cosine of my angle. So what's going to happen here is I have one vector there, another one there. This is finding the angle between them, I guess usually the smaller angle. All right. So let's see the dot product. So if I dot 2, -3, 1 with 5, 1, -1, I get 10, -3, and -1. So 10 minus 4 is 6. And at the bottom, I do the magnitude of A. The magnitude of A comes out to a 4 plus 9 plus 1, so square root of 14. And then the magnitude of B, I get the square root of 25 plus 1 plus 1, so square root of 27. So if I multiply those together, I get the square root of 378. Oops. So then I go into my calculator, and remember we do arc cosine of 6 over the square root of 378. Make sure you're in degrees, and that will get you your angle, which is 72.02 degrees. Okay, so that seems to make sense right there, like that angle right there, 72 degrees. All right, now with parallel vectors, when you have parallel vectors, the angle between them should be nothing. They're flat, like on top of each other. All right, so let's just make up a couple. Like let's have the vector 2, 3, and we know parallel to that, multiplied by 2, I get 4 and 6. Remember, the way to prove parallel vectors is to prove that they are scalar multiples of each other, or to know that. So if I do my cosine of my angle, the dot product of these two things would be 6 plus 18, so 8 plus 18, 26, over the magnitudes multiplied together. Well, the magnitude of the first one is square root of 13. The second one is square root of 52. But when I put those together, I get square root of 676, and the square root of 676 is 26. So what I end up with is cosine of my angle is equal to 1. So remember, your good old trigonometry, when you're on the unit circle, you got 1, 0 right here. And the cosine of the angle is the x value. So when is a cosine 1? Well, hey, guess what? It's when the angle is 0 degrees. Okay? All right, and then perpendicular vectors. So do you remember from before, maybe we didn't talk about this before. Yeah, because we're just introducing dot product right here, sorry. Getting confused. So perpendicular vectors, what would happen to you here is that this piece over on the right side, if you were doing this formula, you would get 0. So let's see why. All right, so perpendicular vectors. So let's have two vectors. One of them is 2, 3, and let's have the other one be -6, 4. So I'm just going to graph those like in 2 dimensions, all right? So if I had 2, 3 over 2 and imagine up 3, so a vector like that. And then my other vector was -6, 4, so -6 a little longer and 4 right there. All right, so let's look at that right there. So they are perpendicular, even though my drawing kind of stinks. This is a perpendicular right here, all right, a 90-degree angle. So let's do their dot product, A dot B. If I do their dot product, I get -12 plus 12. So that's a fact that dot product of two perpendicular vectors is 0. So if I go ahead and put that in my formula, cosine of my angle, I would have 0 over, I don't even care what the magnitudes are, doesn't matter, it's just going to be that when is the cosine of my angle equal to 0. And guess what? This point up here, 0, 1, well, that's when it's 90 degrees. Okay, so my angle is 90 degrees. So that's 2 things you have to know right here, that parallel vectors are scalar multiples, perpendicular vectors, their dot product is equal to 0. All right, direction angles. So a direction angle is going to be the angle that your vector makes with the x, the y, or the z axis. So like this alpha right here, if you have that red vector and you're saying what's the angle back to the x-axis, here's beta, so it's kind of off center in a way, but it's the angle back to the y-axis, and then of course you have the z-axis right there. And if I'm not mistaken, this letter right here is gamma. I'm just going to call it that because I can't remember if it is, but whatever. All right, so a couple of things to note right here. So we're going to have a vector A, and it's made up of A1, A2, and A3. So these are basically my x, y, and my z. If I talk about vector I, remember, is your standard vector in the x direction. It's 1, 0, 0. And j would be 0, 1, 0. K would be 0, 0, 1. All right, so let's look at this guy right here. Here's my formula, kind of like before. So I'm going to dot vector A. That little 1 should not be there. If I dot vector A with I, look what happens. this creates a 1, but these two just cancel out. All right, so what's going to happen is this just becomes a 1, the first part of my vector, and at the bottom, what's the magnitude of this? Well, the magnitude of this vector, it's a unit vector, so the magnitude's 1, so why bother with multiplying something by 1? We're just going to leave this as magnitude of A itself, so that 1 should also not be there. Sorry about that. All right, so similarly, if we want the other angles, cosine of beta, that would end up being a2 over the magnitude of A again, and then cosine of gamma is going to be a3 over the magnitude of A. All right, so find the directions angle of this vector right here. So let's see, cosine alpha, I'm going to do a1, so -2 over the magnitude of this thing. The magnitude of A is going to be square root of 4 plus 1 plus 25. All right, so that would be 30. All right, so you get your calculator and your angle comes out to 111.4 degrees. All right, cosine beta would be 1 over the square root of 30. And then beta comes out to be 79.5 degrees. And cosine of gamma, you finish that one. All right, so when you do this, you end up getting 5 over radical 30. And so your angle comes out to 24.1 degrees. Okay. All right, we are skipping this example here and moving on to something called projection. Now, hopefully you did projection in pre-calculus class, but this is basically a couple formulas that we have to do, and I'm just going to explain it like real quick. So what happens is you're traveling on a surface, okay? But the force with which you are traveling, like the force that you're acting with on that surface is like this, is going off that. So it can be either picture here, like this one's going up like that, here's your surface, here's my surface, and here I am trying to go that way, okay? So oftentimes what you want is you want to know the component of your vector, the part of the vector that's acting in the direction of the path that you're traveling on. So that's called the projection. It is the projection of how you're trying to go onto the surface that you are traveling on. So it's almost like the shadow of your vector in a way. And then if you need to, you can also find the perpendicular component to that, because whenever you have a vector, when you have a vector, you have one piece and then you have its perpendicular component. And those two actions make up that vector right there. Okay? So anyway, the projection finds you the vector along the path or along the thing that you're traveling on when you have a certain force that you're acting with. All right, so that's the general idea. And so when you're doing projection, you say the projection of B onto A, because you're projecting your action onto that angle right there, or onto that surface. All right, so we have two things that we have to learn here. We have the first one is literally the projection formula. So when somebody says a projection of B onto A right here, that's formula. So notice I have A dot B, I have magnitude of A squared. This is all numbers, but then I have another vector right here. So this is going to produce a vector. Whereas if somebody asks you for the scalar projection, remember scalar means just a number. And so that's called the component of B onto A. And notice what it gives you. You have a dot product over a magnitude. This is just a number. So the component is basically just the length of the vector, the length of the projection vector. So this right here is the length of that. Okay. All right, so let's try it. So we're finding the composition of y onto x right here. All right, so basically I'm going to do x dot y. And if I look up my formula, whatever was down here is right there. So I'm going to have x magnitude. All right, so x dot y. So if you dot these together, you get 6 plus 3 plus negative 12. So 9 and negative 4. So 6 plus 3 plus negative 4. So 9 minus 4 is 5. So I get 5. And the magnitude of x, I get 9 plus 1 plus 1, so it's 11. So square root of 11. So there we go. All right, so let's be a little tricky here. My projection vector, all I do, the only difference between this and this piece right here is I square the bottom. So why don't we just use what we did? We have 5, and let's just make that 11. And then I need vector, whatever vector was down here, I need up there, so that was x, so I need vector x right here. 3, 1, 1. All right, so I end up getting 15 over 11 for this vector. I get 5 over 11, and I get 5 over 11 again. Okay, so that was the projection of y onto x. And if you did the magnitude of this thing, if you did the magnitude of this vector, it would come out to this answer right here. Okay. All right. So next one. So next we have last little thing, work. So you do this in physics sometimes, and so there's one use of projections occurs in physics when calculating work. Work is done by a constant force in moving an object through a distance, d. So work equals F times d. But this applies only when the force is directed along the line of motion. So like, for instance, in this picture here, you have a wagon going this way, and let's say you were down here, you know, pushing the wagon, and you were on that same plane or whatever. Well, that's not always the case, because like you see in this picture, you're really up here, we're going to be like pulling the wagon along this 35-degree angle. Okay, so there's two different situations, and so two different formulas for work. So when there is a formula, an angle that you're pulling at, you use that formula. When there is, when you're pulling or the force is acting in the same direction that you're going, you use this one right here. Okay. All right, so let's do the first one. These are our last two things to do. So I need my work is my magnitude of my force, so the strength with which I'm pulling something, times the distance that I go, and the cosine, the angle of my force. So my force in this one is 70 newtons. My distance that I'm going is 100 meters, and cosine of 35 degrees. So I plug that in my calculator. That means my work done is 5,734 Newton meters, because remember I had newtons and meters, but those are called joules. So you can say 5,734 joules. I think it's Joules, right? And the last one here. So this one says a force is given by this vector and it moves from there to there. So all I need is like a distance, or like a direction vector. So I need to figure out the direction if I'm going from P to Q. I just need a vector to represent that. So I think of a component form. 4 minus 2 is 2, 6 minus 1 is 5, and 2 minus 0 is 2. So all I have to do is dot this with this, and that will give me my work. So my work, if I dot those, I get 6 plus 20 plus 10. So I get 36 joules. All right, and these problems are not to do right now. They're just, we're going to start them in class, but